Okay, if you're given impulse response HT, we can find the output corresponding to any input using the convolution integral. Okay, so today what we are going to discuss is we can if you are given the impulse response of a system, how to determine the properties of that system from the impulse response. That means properties means memory, causality, stability, invertibility. These are the properties of systems that we have discussed. So today we'll discuss, see how these properties, we can determine these properties from the impulse response of the system. So let us start with a discrete time system. We have a discrete time system having impulse response Hn. Let's say Xn is the input, Yn is the output. Now what is the convolution summation? Yn is xk Hn minus k. That is the convolution summation. Now since the convolution operation is commutative, we can interchange, this is Xn convolution Hn. Since the convolution operation is commutative, we can interchange that order. This is same as is it true? I'm using the commutative property of convolution. Okay. Now I am splitting the summation. I am writing this as, okay, this is left hand side, it is Yn. So here it is Xn H0 plus Xn plus 1 H minus 1 this is the summation, this is the convolution summation. I am expanding this like this. Okay, there are infinite number of terms because it is k minus infinity to infinity. So I have written here 1, 2, 3, 4 terms. There are terms on both sides. Now what about this term? We are trying to find the output Yn. If we want to find some instant of time n, this is the output, isn't it? Now, can we say that if you want to find some instant, the output at some instant n, this is the present value of the input, is it? And what are these values? These are functions of what? Xn plus 1 is what? We are trying to find input at an instant n. Then what about n plus 1? Is it past values or future value? Past values or future values?
Future values.
So can we say that all these terms they contain future values of the input? And what
Yes,
about
sir.
the terms on the left hand side?
Past values.
Past values. Okay. Now let us come to the property. What is a memoryless system? What is a memoryless system?
Depends only on present value.
If the output at any instant of time depends only on the input at that particular instant of time, then we can say that the system is a memoryless system. Is it? And that condition must be satisfied for all the possible signals. It is not that for one signal that condition is satisfied and some other signals that is not satisfied. If that condition is always satisfied for all the signals, then we can say that it is a memoryless system. Now, can you tell me what is if you are given Hn, the impulse response of a system? Can we determine whether it is a memoryless system or not? What is the condition? When can we, from this summation, can you say what is the condition for that system to be memoryless? Can we say that in the summation all these terms must be 0 and these terms must be 0? Is it?
Yes, sir.
Then only the system output depends only on the input at that particular instant of time. All these values should be 0 and all these values should be 0 for any signal. Then what is the condition for that system to be memoryless?
H of n is in terms of delta n.
Can we say that h of n is 0 for n not equal to 0? Is it the condition? If this condition is 0, if this condition is satisfied, that means the impulse response that is 0 for n not equal to 0. All these terms in the summation will always be 0. So only non-zero term will be this one. Is it? So that is a condition for a system to be memoryless. If you are given the impulse response, we can easily identify whether it is a memoryless system or not. The condition is that Hn must be 0 for all the values of n other than 0. So can we say that the general form of a memoryless LTI system is some constant times delta n? Is it that? This is the general form of an LTI, memoryless LTI system. Is it that? Is there any other form possible? If the system is sorry? No. Isn't it?
No,
So now can you tell me what is the possible operations of a memoryless LTI system? If impulse response is k times delta n, what will be the output? Yn is what? It is xn convolution k times delta n. What is that? What is that convolution? It is k is a constant. Is it k times what? Xn convolution at delta n? What is that? Xn convolution delta n. If you convolve any
Xn.
signal with delta
xn.
delta function, you will get xn.
Zero.
So what is this operation?
scaling.
Same part. It is, we can say that it is amplitude scaling, isn't it? Is it that? Amplitude scaling. We are scaling the amplitude with a constant factor or simply an amplifier. Is it that? So this is the only operation possible with a memoryless LTI system. You cannot do any other operation. And remember, this is only for if the system is LTI. If the system is not LTI, you can do many operations. There is no issue. But this condition, if the system is LTI, then this is the only operation. For example, if you consider a system xn2, this is not an amplifier. This is taking the mode. You can say that it is a rectifier. You negative values also you'll get positive output. Is it an LTI system? Is it a linear system?
No, sir.
No, it is not a linear system. So if the system is not linear, you can have many other operations. There is no restriction. But if the system is linear, then only possible operation is amplitude scaling. Amplitude scaling with a constant factor. Okay. And same thing we can easily prove for continuous. Okay, before discussing that, let us discuss the next property. What about causality? When can we say that if you are given h of n, can we say whether the system is causal or not? What is the condition
Yes, sir.
for causality? Causality means
Sir, Hn is equals to 0 for n less than 0.
n less than 0. Causality means the system output must be the system output at any instant of time that should depend only on the past and present values, not on the future values. It should not depend on the future values of the input. So if you consider this summation, you can see that out of these are what? For past values, isn't it? Xn minus 1, next term is xn minus 2. These are past values, but these are what? These are future values of the input, n plus 1, n plus 2. So this term should be 0 for all the values of n. Then we can say that the system is a causal system. This term should not come in the summation. This should be 0. That condition is that is it hn is 0 for n less than 0? Then we can say that the system is causal. Is it? Is it the condition?
Yes, sir.
Now we can prove this the corresponding these properties for continuous time system. The continuous time interval integral is yt okay. So the properties are similar. If the system is memoryless, then ht is a constant times delta t. That means the impulse response should be 0 at all the instants other than t is equal to 0. Only at that point it is non-zero. That we express with this function k delta t. Now, then we can say that the system is memoryless. Okay. Now, what is the condition for causality? Causal. It is ht is 0 for t less than 0. Then we can say that the system is causal. It is similar to that this one discrete time case. So here it is a discrete time signal. Here it is a continuous time signal. Impulse response. Okay. What is a causal system? The output at any instant of time should not depend on the future values of the input. Now, what is this impulse response? What is impulse response of a system? You are given an LTI system. What is impulse response? What is the definition of impulse response? It is the
For
output.
the input being delta function, what's the output?
You are giving delta n as the input. Measure the output, that is hn. That is the impulse response. Now, what is this delta n? Is it the signal delta n? I am talking about a discrete time signal. Is it the signal delta n? It is 1 at 0. So this definition is intuitively satisfying also, because here we are giving the input at 0. So what is causality? The output at any instant of time should not depend on the future values. So we can say that the output should not occur before we apply the input, isn't it? The input starts from here. Here it is only one sample. So the output also should start only after that point. That is this condition. Hn should be 0 for n less than 0. Okay. That is the condition for causality, and we can easily verify these conditions graphically also. Let me explain that. If you consider a signal, let's say this is the signal xt, and its impulse response is, let's say this is the impulse response of the system. Consider an LTI system. This is the impulse response. I am marking these values like this because these are the values less than 0 and this is greater than 0. Now, if you want to find the output at some instant t naught, what is the procedure, graphical procedure? We have to flip this signal. When you flip this signal, is it like this? This is the flipped version of the signal. Which point is this?
So T.
This is t. And if you want to find the output at t naught, where will be this point? This point means 0. We have to move that point to t naught. So will it be t naught? If you want to find the output at any instant of time t naught, is it? Flip this signal, then move this point to whichever instant we want to find the output. That is the graphical procedure. Now, if you want to find the output, this one, multiply these two signals, find the area. Is it? Now, if you consider if you want to find the output at this instant of time, with respect to this, these are the future values, isn't it? These are the future values of the input. If you find the input at this output at this particular instant of time t naught, these are the future values and these are the past values. Now, this portion is multiplied with this, isn't it? And these past values are multiplied with this. Is it? Now, what are these values of ht, that impulse response? Is it this portion? After flipping, it will come here. Is it this? And what are these values? Is it ht less than 0? Negative values of t. So the condition is that if the convolution is if it does not depend on the future values, then this part should be 0. Okay, this part should not come. So this part should be 0. Then only if you multiply these two, it is always 0, isn't it? The output will not depend on the future values of the input. The same condition you can prove graphically also. Okay, so now we can extend this result. There are some important properties. Suppose we have a linear time in where we can prove these properties graphically. Suppose we have a linear time invariant system ht, and if the system is causal, okay, we have a causal linear time invariant system. That means ht is 0 for t less than 0. For negative values of t, ht is 0. Now suppose we are giving an input to the system, and the input is such that it is 0 up to some time instant t naught, and then this one. Okay, the input signal is 0 up to t naught, then some signal. Now what about the output signal yt? Does it have the same property? The output is also 0 up to that particular instant of time t naught. Is it true?
Yes,
How can we prove that?
so because it depends on the past values, and the past values and present values are 0.
No, it
So
is
my
not.
current-
I'm saying that the system is causal. System is causal means its impulse response. Take any arbitrary impulse response. This portion must be what? If you consider
Zero.
ht of an impulse of a causal system, this must be 0. Is it?
Yes.
And it can be 0 for more than t0 also, but this must be 0. Okay, if that is 0, then after in the convolution operation, you have to flip it. And if you want to find output at some instant of time t, this is the point t, isn't it? Is it? Sorry, this is the flipping of this signal. Okay, this impulse response. This is ht minus tau. Now, what is the convolution operation? We move this point from minus infinity to infinity. So, can we say that if this portion is 0, until this t reaches t naught, the output is always 0? Is it true? Because this is always 0. For a causal system, this is negative. For negative values of t, ht is 0. When you flip it, it comes like this. This is the point t. This is always 0. It can have some non-zero values like this. Now, if we move this point from minus infinity towards right, and you multiply these two signals, find the area. That is the convolution operation, isn't it? Now, until this point reaches t naught, what will be the output?
0.
It will be 0 because it is multiplied with this non-zero part of the signal is multiplied with 0. So it is always 0. So can we say that if the input is 0 up to some time instant t naught, output is also 0 up to that instant of time? If the system is causal. If the system is non-causal, that may not be satisfied, because for a non-causal system, let's say something like this. So if you take this is a non-causal system, so where will that overlap start? Let's say this is -1. So this is t plus 1. So the overlap starts at which point? If it is non-causal in this particular example, until this t plus 1 reaches where? T naught. That is where is that? Is it T naught minus
1.
T naught minus 1? Okay, the input starts at T naught, but the output starts at T naught minus 1. That is possible only if the system is non-causal. If the system is causal, it is same. Okay. And there is another property related to this. I am leaving it as an exercise for you. Please prove this. You can easily prove it using the graphical method. There is some issue. Okay, now it is moving. Okay, so the property is that if you have an LTI system, let's say HT is the input to that, HT is the impulse response of the input system to the impulse response of that LTI system, and let us assume that the system is a causal system. Okay, causal means HT is 0 for t less than 0. Then the property is that if you are giving a signal x1t to this system, you are giving two separate inputs, x1t and x2t. If x1t and x2t are such that both the signals are same up to, let's say x1t is something like this. I'm just giving an example, x2t. Okay, that means both the signals are same up to this instant. Let's say this is some time instant t1. Both the signals are same up to this instant. The shape may be different. I am just, for simplicity, I am drawing a constant signal. Now, can we say that if the system is causal, the output for these two signals will also be same up to this time instant?
Yes, sir.
Is it true? You can easily prove that. I am leaving it as an exercise. And okay, so now let us discuss the next property. Next property is the stability property. What is the condition for stability? Stability of a LTI system. When can we say that a system is stable? What is the condition for stability?
Finite input gives finite output.
If the output, we discussed about a particular form of stability that is called BIBO stability. Okay, BIBO means bounded input should give bounded output. Then we can say that the system is stable. That means if you consider a continuous time system is bounded, we can say that it is less than or equal to a maximum value that is finite. Then we can say that the input is bounded. If the input is bounded, and if you are giving a bounded input to a linear time invariant system, this condition must be satisfied. Some by it should be finite. Okay, then we can say that the system is BIBO stable. Now let us let us see whether we can determine this property from the impulse response of a system. If we are given impulse response, this is the relation between the input and output in terms of impulse response. Isn't it? And using the commutative property, we can write it as -infinity to infinity h tau xt minus tau d tau. This is the input output. So suppose the input is bounded. We are given the information that the input is bounded. How to check whether it is BIBO system or not? We have to find whether this is bounded or not. That is this one, isn't it? can we write this as less than or equal to minus infinity h tau xt minus tau d tau? This one? Is it that? I'm taking the mode inside the integral, so then this will become less than or equal to. So this is less than or equal to minus infinity, because mode of ht into xt minus this one. Okay, so this is this one. So this is minus infinity to infinity h tau mod xt minus tau d tau, isn't it? Less than or equal to. Now we are given the information that this is bounded. Can we simplify this? If the input is bounded, is it, what is the maximum value of xt minus tau? Is it bx? We are given the information that the input signal is bounded. If it is bounded, can we write like this? It is less than or equal to minus infinity to infinity h tau d tau. Is it? Is it possible?
Yes, sir.
Yes.
Yes.
Now tell me, what is the condition? If the input is bounded, we get this relation. Mod yt is this. If this has to be bounded, then what is the condition? This must be, this is finite. If this is finite, then it is bounded. Is it? So what is the condition for stability?
Impulse response, the area under impulse response is bounded.
It is not the area under impulse response. This is important, this mode. Okay. This is the condition for stability of a system. Integral minus infinity to infinity h tau d tau. This should be finite. So we can say that the impulse response must be, this condition is called absolutely integrable. Absolutely integrable. That means it's mod ht, that area under that should be finite. Then we can say that the system is stable. Okay. Same condition, similar condition for discrete time system. There the only difference is, so you can easily verify that condition is, it is the only difference is that this here it is an integral, there it is a summation. The condition is summation. Let's say we can write it n also, h of n minus infinity to infinity. It should be absolutely summable. Here it should be absolutely integrable. This is the condition for discrete time system. Then we can say that the system is stable. Let us consider an example. Consider this system xt to integral minus infinity to t x tau d tau. This is an integrator. Okay. Is it a stable system? What is the impulse response of this system? This is yt, the output. If you are giving xt as the input, okay. If you are giving xt as the input, its integral is the output. It's an integrator. What is the output? This is yt. What is the impulse response of the system?
U of t. Unit step function.
It is u of t. To find the impulse response, you just substitute xt is equal to delta t. So this this impulse response ht is, in this case, is integral minus infinity to t delta tau d tau, isn't it? What is that? Integral of delta function is ut. We have already seen this. Okay. So if the impulse response is ut, then it is always the system output is integral of that. That is also very easy to verify. If xt convolution, this is the output, isn't it? Ut. What is this? Integral minus infinity to infinity x tau. What is this convolution? Xt convolution ut. Integral minus infinity to infinity x tau that is ut minus tau d tau. That is the convolution integral. Now, is it same as this? Are they same?
Yes,
Here it is minus infinity to infinity, minus infinity to t. It is same because when will this be non-zero? Ut minus tau. It is non-zero when the argument is greater than what? What is
When
unit step
t
function?
minus tau is
It
greater
is
than 0.
when t minus tau is greater than 0. Okay, and here the variable is tau, so it is the same condition. Till tau is t, this one. So these two integrals are same. Okay, anyway, so we have seen that ht is ut. Is it a stable system? Is it a stable system? What is the condition for stability? The impulse response must be. Is it the condition for stability? The impulse response must be absolutely integrable. That is the condition we have proved here. This is the condition. If this condition is satisfied, if this term is finite, we can say that the system is stable. So what is the condition here? Is it a stable system?
No.
No, because area under unit step is not finite. It is finite. It is a ramp function. It is not a bounded signal. If you integrate this mode of this, you will get a ramp function. It is not bounded. As t tends to infinity, its amplitude tends to infinity. It's not a bounded signal. Okay, bounded output. So this is not a what? It is not a. It is an unstable system, isn't it? Okay, that's about the stability. Now let us discuss the next property, that is the invertibility. What is inverse system? Suppose we have a linear time invariant system. When can we say that the system is invertible? When can we say a linear time invariant system is invertible? If we are giving this as the input to what? If you are giving this as the input to a second system, that is called the inverse system. And if we can get back this signal, if this is xt, then the system is invertible. If we can find a system such that any input, you'll get the same signal here, then we can say that if this is satisfied for all the possible signals, then we can say that the system is invertible. And this is h inverse t. That means I'm assuming that it is anyway, for a time invariant system, its inverse is also a time invariant system, LTI system. So let's say this is the impulse response of that. Now what connection is this?
Cascade.
It is a cascade connection. Now can we replace it with a single system? What is impulse response? Is it ht convolution h inverse t? Is it that?
Yes, sir.
So here you give xt, you will get xt here. That is invertibility. What should be this?
Delta T.
That should be a delta function. Then only whatever signal you are giving, you get the same output here. So the condition for invertibility is ht convolution h inverse t. That is the impulse response of the inverse system. If we can find a system such that this condition is satisfied, then only we can have the system is invertible. Okay, let us consider a simple example. If you consider a system xt to, let's say, xt minus 2, what does this do, this system? give any signal, it output is a delayed version of that signal. What is the impulse response of the system? We are considering a system, linear time invariant system. The system is such that whatever input you are giving, the output is delayed, that input delayed by 2. What is the impulse response of the system? How to find the impulse response?
Del t minus 2.
So if you give delta t,
Delta function of t minus 2.
delta t minus 2, isn't it? That's why if you convolve xt with delta t minus 2, what will be that? Xt minus t naught. Is it an invertible system? Is it an invertible system?
Yes, sir.
What is the inverse operation? Here you are shifting left by 2. The inverse operation is shifting what?
Right by.
Sorry, this is shifting right by 2 and inverse operation is shifting left by 2. That is time advance. So what is the impulse response of that inverse system? Shifting left by 2. What is input?
Del t plus 2.
This del t plus 2. So you can see, verify that del t minus 2 convolution. What is this? This is delta function delayed by 2. You are convolving with a delta function advanced by 2. So this will be shifted. This is a delta function shifted right by 2, isn't it? Now if you convolve it with a shifted delta function, is it delta t? It is property of delta function. Okay, so this is the inverse system. xt minus xt minus 2. Let's say this is a system. We have to find the impulse response of the inverse system. That is the question. Given this system, this is the system. What is the impulse response of the inverse system? What is the impulse response of this system? What is the impulse response of this system?
Delta t minus delta t minus.
Impulse response means you have to give delta t as the input. What is the output? That is, the impulse response is denoted by ht. Is it this? If you are giving delta t as the input, if you are giving delta t as the input, then what we get is delta t minus delta t minus 2, input minus delayed version of the input signal. That is what the system does. Now what is this? This is what?
The impulse response.
This is the impulse response of the system. We denote it by ht. That is impulse response of the system. Now what is the condition for invertibility? Condition for invertibility is when we convolve this ht with the impulse response of the inverse system, when we convolve this with the impulse response of the inverse system, we should get delta t. Is it? Now can we find the we know this ht. Can we find this? Suppose this is the impulse response of the inverse system. What is this convolution? We are given that st is this. So this convolution is delta t minus 2 convolution is it this condition? I am substituting this here, st here. Now can we simplify this convolution? Can we simplify this convolution?
H inverse t
Distribute.
minus H inverse t minus 2.
If you convolve the impulse function with any function, you will get the same function, and delayed function means delayed version of that function. So this is h inverse t minus h inverse t minus 2. This delayed by 2, that is delta t. Okay. So if we rearrange this, what we get is h inverse delta t plus h inverse t minus 2. Can we write this as with that?
Yes, sir.
So what I did is like this h inverse t minus 2. You put t is equal to t minus 2, you will get that, isn't it? If you put t is equal to t minus 2, you will get h inverse t minus 2, that is equal to delta t minus 2 minus h inverse t minus 4. So you'll get this. Put that value here. Now if you keep on doing this repeatedly, what will you get? Is it something like this? Delta t minus 2 plus delta t minus 4. Is it like this? I'm replacing, this is h inverse t. H inverse t. So this is h inverse t minus 4. What I'm doing is putting t is equal to t minus 4 here. Find the value here. Replace this h inverse t minus 4 with that value. And if you do it, if you keep on doing that, you will get this. And we can simplify that notation, that is k minus infinity to, sorry, k from 0 to infinity delta t minus 2k. Is it that? And this is called an impulse train. Impulse train, if you sketch this, there is an impulse at 0, next impulse is at 2, 4, and this is the impulse response of the inverse system. Now, how can we verify that this is indeed the inverse, the impulse response of the inverse system? When we convolve this with ht, what should we get? We should get delta t, isn't it? What is ht? What is ht? Is it delta t minus 2? So if you convolve this with delta t minus 2, will you get delta t? If you convolve this with delta t minus 2, will you get this? Delta t?
Yes, sir.
You will get that because the first term is convolution with delta t, you will get the same impulse train. Then when you convolve this with delta t minus 2, this will be shifted right by 2. So, and when you subtract that, you can see that everything, all these impulses will get cancelled. Only this will remain. That is delta t. Okay, so this is the impulse response of the inverse system.